Hi everyone, Fight here, and welcome to part 3 of the Operating Systems Concepts video series. In this video, we'll talk about processes. We'll talk about how you can create new processes, wait for existing processes, and communicate between two processes. As usual, we'll be using C, and the code we write here will be applicable only to Linux and Mac, or any Unix variant. If you're on Windows, sorry, but you're out of luck. Alright, let's dive right in. Here I have a directory with just a make file. If I open up the make file, it just has a few targets for files that we'll be writing in this video. The first thing I want to show you is how processes can be created. So let me just write a new program called main.c and open this up. And here I'll write our standard function signature int main. Now the first thing I want to do is talk about what a process is. A process is basically like an instance of a program. You know, when you open up a new terminal, for example, your computer is creating a new process with that terminal running in it. Every time you run a command in your terminal, your operating system creates a new process. You may hear the term fork, which is just a verb that means from a parent process, create a child process. As we'll see shortly, there's a fork syscall in UNIX that does exactly this. From a parent process, it creates an identical child process. And then you can do different things with the child process. So let's explore this further. Let's see how we actually use the fork syscall. Fork is a little bit tricky, because whereas we're used to thinking about single-threaded programs, as in you execute one line of code, then the next, and one after that, and so on, fork is a bit tricky because it creates two processes that are identical, so they both start executing code at the same point. So let me show you what I mean by that. If I simply type fork, and then I type printf hello, after the fork instruction, you'll have two processes. One is the original parent process, and one is a new child process that your operating system created when you called fork. So there will actually be two processes, both of which are completely independent, that both reach this printf statement, and so they would both print hello. So on your console, when you run this program, you would see hello printed twice. So let me try that out, but before I do, I need to import some things, so let me add some imports. Okay, I've added a few include statements. I've also included some things that I don't use yet, but I will shortly. And so let me save this program, and let's compile it, and then let's run it. And you can see, as expected, that hello gets printed twice. So this is kind of tricky, right? From looking at this code, you would only expect one hello to be printed. But actually, since fork creates two identical processes, both of which execute the code after fork, you actually get hello printed twice. So this is great. We can create two identical processes. But what if we want the parent to do one thing and the child to do something else? In order to do that, we need to know if we're in the parent process or if we're in the child process. The way we can figure that out is by looking at the return value of fork. So let me create a new variable called child PID. A PID is just a process ID. That's what PID stands for. Now the fork syscall does different things depending on whether you're in the child or the parent process. If you're in the parent process, fork will tell you the PID of the child process. So I can say child PID equals fork. And so if I'm in the parent process, child PID will be set to whatever process ID the child process gets. However, in the child process, fork will always return a value of 0. So if we check the value of child PID and find that it's 0, then we can know that we're in the child process. So let's wrap that up in an if statement. So I'll say if child PID equals fork equals 0. So everything inside this if statement will only be executed by the child process. I can add an else statement and say everything in here will be run by the parent process. Again, fork will return 0 if we're in the child, so we'll enter this if block. If we're in the parent process, however, fork will return a positive number if things went okay, or a negative number if there was an error forking the process. So this way, we have a way to distinguish between the child and parent processes. Alright, so we've seen how that works. Now, let's talk about one way two processes can communicate, and that is a very simple mechanism, but it's one that we've already talked about in the first video, which is through the exit status. Every process has an exit status set when it terminates. In our example, the return from main indicates that we'll return an exit code of 0. You can also call the exit syscall to return with a particular exit code. So let's try that now. In the child, let's just call exit, and let's put in some number, let's say 12. And so this says, if we're in the child process, exit with an exit code of 12. Now in the parent process, I want to be able to check for that exit code. To do that, I need to wait for the child to terminate. So I'll use the wait PID syscall, which says wait for a process with the given process ID to terminate. So the way that looks is wait PID, and I'll pass it the PID that we want to wait for. In this case, we want to wait for the child process, so I'll give it child PID. Okay, now we need to give the operating system a way to tell us what the exit status of the child was. So the way Unix does that is by taking in a pointer to an integer that's called the wait status. So let me create an integer called wait status, or W status for short. And now in the wait PID syscall, I will pass a pointer to the wait status integer. So this tells the operating system put all the information about the child process into this W status integer. And then there's a last argument that specifies what you can do. For example, if you don't want to block the parent process, but you just want to check for the child process, you can pass in some options, but I won't go over them here. If you want, you can look at the man pages for the wait syscall and see what the options are. Okay, I pulled up the information about the wait PID syscall. Here are the options that I was mentioning earlier. These control the way the wait syscall works. But what I'm interested in here is this W exit status macro. So the W status integer that we passed in earlier contains 32 bits, but the wait status is usually a number between 0 and 255. So it's actually only 8 bits. So your operating system assigns 8 of the 32 bits in W status to the exit code of the child. The other bits indicate other information. So let's just try using the W exit status macro. So I'll go back to my terminal and say, let's say printf child exited with status integer, new line. Now let's call W exit status on W status. So this basically just extracts 8 of the 32 bits that correspond to the exit code. So I'll save that, and let's save and quit, and run make, and let's run main. And you can see there that child exited with status 12. So it's working as we expect. So this is a really simple way for two processes to communicate, but it's not really that good. You can only communicate when one process exits and signals with the exit code. So let's talk about another way two processes can communicate by exchanging a stream of data. Unix provides a concept known as pipes, which are really common in the terminal. For example, if you've ever seen the pipe symbol like this in your terminal, that's a Unix pipe. And basically it sends the output of one process to the input of the next process. But pipes are more generic than that. They don't necessarily have to deal with standard input and output. Let's look at an example of how to create a pipe between two processes. So I'm going to make a copy of main.c and call it pipes.c. Okay, the syscall you use to create a pipe is simply called pipe, and here is the manual page for it. You can see that the pipe syscall takes in an array of size 2 of integers, and what this does is it creates 2 file descriptors and stores the results in that array. The way a pipe works is there's a read end and there's a write end. So typically you have one process writing stuff into the write end of the pipe, and the other process can read from the read end of the pipe, and it'll see whatever sequence of bytes was written into the pipe. So the way you create a pipe is by calling the pipe syscall and passing in an int array of size 2. Basically, the pipe syscall will then allocate 2 file descriptors and store the results in that array. The first element of that array will be the read end of the pipe, and the second element of the array will be the write end of the pipe. So let's see how that looks in code. I'll go over here and let's create an array to store our pipe file descriptors. Let's say int fd for file descriptor. It has size 2. And then let's call the pipe syscall. So we can do pipe fd. We should also check that there's no error when we call the syscall. So we can do, if this returns a negative number, we should just exit the program. So we'll say return 1. So this will exit with exit code 1, and that indicates that something went wrong. So another important point about processes is that they inherit file descriptors. So when you fork a process, the child process has access to the exact same set of file descriptors as the parent. So the child will have access to both the read end and the write end of the pipe. In this case, I want my child process to simply read from the pipe and print what it gets to standard output. So to avoid any confusion, let's close the write end of the pipe. Remember that the write end of the pipe is the second element of the array, so that's fd1. So fd1 is the file descriptor corresponding to the write end of the pipe, and in the child process, which is only reading from the pipe, I want to close the write end. Okay, now in the parent, let's do the same thing. In this case, we're going to be only writing to the pipe, so let's close the read end. So we can do that like this. Alright, now let's actually write something to the pipe. So let's just make a new string, let's say hello from a pipe. And then let's write it into the pipe. The way we can write into a pipe is the way we can write into any normal file descriptor. If you remember from the first video, the write syscall lets us do exactly that. So we'll call write, and we'll write into the right end of the pipe, so that's fd1, and we want to write in the message hello, hello. And we want to write in @stirlen hello bytes. So let's do that. Alright, now the child lets read from the pipe. Again, the pipe is just a normal file descriptor, so we can call the read syscall. Remember that the read syscall needs a place to put the data, so let's declare a buffer of size buff size. And let's define the constant buff size up here. Let's say it's 128 bytes. And then let's call the read syscall. So we'll say the int bytes read is equal to read. We'll read from the read end of the pipe, which is fd0. We'll read into buff, and let's read in @most buff size minus 1 bytes. And then remember that read returns a negative or 0 number if there was an error or if we don't have anything to read. We can check if bytes read is greater than 0. If so, let's add a null terminator to the end of the buffer, like so. And then let's print it out. So printf %s with a new line, and let's print out the buffer. Okay, this should work. And then let's change the exit to 0 since we're exiting normally. And this should just work. Technically, we should also maybe close both sides of the pipe once we're done. But our operating system will probably clean it up, and so it's not a big deal. So let me save this and quit. Let's type make. And it's saying I forgot to import string.h, so let me do that real quick. Alright, let's save and quit, run make, and then let's run pipes. And there you go. You can see that it printed hello from a pipe. The child exited normally with status code 0, and then we had that leftover hello statement in our main function. Cool. So hopefully you learned a little bit about how processes work and how you can communicate between two processes. Most programming languages have a concept of processes and threads, which we'll discuss later. But note that what some programming languages call a process may not exactly correspond to the operating system level process that we discussed in this video. For example, Go has a notion of Go routines, which act like processes or threads, but they don't necessarily map directly to an operating system process or thread. Anyways, hopefully you found this video informative, and I'll see you next time.